Server.
All right. Hi, everyone. Thank you for coming to this session. I know it's late in the afternoon, but we hope that the topic is going to keep you engaged and interested.
Enough to be awake.
Enough to be awake. So my name is Nelly Gustafsson.
My name is Pedro Lopes. We work in the SQL Server engineering group. And today we're here to talk about the newest in database technology that came to be with SQL Server 2017. Out of the gate, you can see several interesting pieces of data here. You can see, for example, a number of achievements we were able to put together for SQL Server 2017. And we start with the one that's the most talked about, that we hear most about, which is the choice of platform and language. So SQL Server 2017 was the debut of SQL Server on a platform that is not Windows. So historically, since back SQL Server 6.5, we've released on Windows. And we have set ourselves a goal in 2017 to be more attuned to the database market. And the database market for enterprises means that you don't sit only on Windows. And therefore, we released SQL 2017 also running in Linux. We support a few distros and also running in Docker containers, which means that you as developers are able to run SQL Server if you're running in your Mac laptop, for example. Your dev machine is not a Windows, that's fine. You can run both the database engine and also tools to accompany that and to manage and to develop on SQL Server. We also have a number of achievements in what relates to performance. In the industry-wide accepted TPC benchmarks, we are the first in TPCH, so that's data warehousing and DSS workloads, both in 1 terabyte and 10 terabytes, and even 30 terabytes. Those are all available in the TPC.org website. You can check them out, how those numbers were achieved. But TPCE also, and we are the first in price performance. Now, security has been one of our obsessions in the past years, and we have already hit a number of breakthroughs in this regard with SQL Server 2016. And from a few years now, both our Azure SQL database and our SQL Server on-premise share the same code path, meaning the same database engine you run in Azure SQL database is the same engine we run in your data center that runs SQL Server there. So being obsessive about security means that, and you can see there for 7 years in a row, we have been confirmed from an independent source as the most secure database that in the market right now. And this is according to the number of discovered vulnerabilities over the course of the last 7 years. Now, I did mention choice of language. And while you see in the left portion of the slide here, we support Python. Nelly is going to talk a little bit about that in what relates to our built-in AI capabilities in what relates to a database engine. This is a breakthrough because SQL Server is the first database product to bring in to AI capabilities on a relational database, meaning you can run you can mine your data, you can run a number of AI algorithms on top of your data using popular R and Python with 2017, and that can be done in memory, leveraging performance at scale. And I'm going to talk a little bit more about our in-memory technology, and then later on, Nelly is going to talk about AI capabilities in SQL Server. And this is available, like I said just a minute ago, across all types of workloads and across all platforms, meaning the choice of platform on-premise, but also in the cloud, be that public, private cloud, and a hybrid model. If you were just in Rohan Kumar's session, he did talk a little bit about how our vision is set on a hybrid cloud because there is no fixed recipe for how your business needs to evolve in what relates to information technologies, and we are right there with you in that perspective. And talking about relational databases, one of our lead competitors is Oracle. And you can just see in this quick animation here how the fact that we have for years set ourselves in a path that we have everything built in, meaning when you license SQL Server, when you get SQL Server, you get all these capabilities under one roof, if you will, under one license. You get BI capabilities, you get AI, you get relational database. And those are all built into the same license. So you don't have to add capabilities and license them on the side. That would obviously be, as you can see right here, leads to a higher TCO, and we strive to be on the other end of this. So with all this intro on what we set ourselves to do with SQL Server 2017 and the modern database, what we want to talk about today is some of the key features in 2017, SQL Server 2017, that will allow you to build more modern applications in what relates to the database layer of those application ecosystems. And specifically, we're going to talk about just a subset of those features, because to be honest, to talk about everything that's on SQL Server 2017 alone would take probably just an afternoon, and just to graze what we've embedded into the product. So, like I said a minute ago, one of the key aspects of SQL Server 2017 was to bring in the choice of platform where you deploy and run your database service. So besides the traditional Windows, we support Linux, and those are the three distros that we support right now: Red Hat, SUSE, and Ubuntu. And we also support Docker containers. Now, on Windows, you can run this obviously on Windows Server, because that would be the enterprise choice in case your shop runs Windows. But you can also run it on your Windows laptop running Windows client, like Windows 10, for example, but also running on your laptop running Mac with Docker container, for example. And we've also strived to make sure the deployment and management of SQL Server in these other platforms is native to those platforms. So it's package-based installation, package-based updates, using the familiar tools and commands to do so. So I don't really want you to read all this fine print. This is just of the some of the new features we've brought into SQL Server as we move from the Windows world to extending to the Linux world. And you can see that there are some gaps in what relates to features available in SQL Server on Windows and Linux. The database engine is the same, literally. It runs the same on Windows, it runs the same on Linux. Now, there are other features that you see on the screen that that have not made it to SQL Server 2017, but we are working to close some of these gaps for VNext of SQL Server. So you see, for example, that on Windows, SQL Server supports Polybase, but not yet on Linux. And then some of the advanced analytics BI tools are only available on Windows, not on Linux. But you see that features that support security, like transparent data encryption, which is encryption at rest, or auditing, for example, are available on both platforms. Or everything that has to do with mission-critical performance, such as in-memory, some of the things I'm going to discuss today, are available on both worlds, if you will. So our first big focus is really the seamless choice of platform. And we've gone through a lot of work to make sure that when you choose to run SQL Server, wherever you choose to run it, you are literally running the same engine that has the same performance and has the same capabilities as a database engine. And just to give you a quick insight as to what we've done, who here has been working with SQL Server or has worked with SQL Server in past editions on Windows? A raise of hands here. Okay, quite a few. Good. So one of the fundamental aspects of SQL Server as a database service has been the abstraction between the underlying hardware and OS that you're running on and the database service itself, the database engine. And that was, for lack of a better word, personified by SQL OS. SQL OS was an abstraction layer that actually turned our high-level commands and T-SQL language into low-level OS requests to get to our I/O, memory management, scheduling CPUs, all of that. Now, that was, because of historical reasons, native to Windows. So we were very tightly integrated with the Windows world. So to extend SQL Server to Linux and other future platforms, if any, we had to do some work here, which is to create yet another layer of abstraction. Now, let me rephrase that, actually. We didn't create another layer of abstraction. We extended SQL OS as a layer of abstraction. And we created what we call SQL PAL, the SQL Platform Abstraction Layer, which allows seamless integration, as you see on the left of the screen there, with Windows, with Linux, and native use of those OS's capabilities. And then the SQL PAL itself, which incorporates SQL OS v2, as we call it, does the translation between Win32-like APIs that we still use to the Linux subsystem. All of this goes to say that we are running the exact same engine, this exact same artifacts and architecture on any current and future OS will be using SQL Server on. And that is to guarantee that you are running exactly the same engine and you are running it to exactly the same expectations as you run your workload, as you are developing code to run on SQL Server. So still in the Linux aspect, we've gone to one of the obvious outcomes would be you that manage SQL Server on Linux and are used to, or better that manage Linuxes and Linux data centers, you have your own set of methods and processes to deploy database services, to update those services and OSs and all of the application ecosystem. So we have a standard package-based installation on all the distros we support, and that makes it very seamless for shops that currently have Linux as their standard OS to incorporate SQL Server into their deployments and their ecosystem. Now, we couldn't do this just based on the core database engine capabilities. So we've also gone in the path of creating cross-platform tools to be able to develop and manage SQL Server. So from command line tools like SQL CMD or BCP for bulk data ingestion, to the tools that like most of this room has worked on SQL Server on Windows, SSMS, you are used to working with that. Well, from a Windows machine, a Windows client machine, you can continue to manage like you always have a SQL Server that sits on Docker or sits on Linux. You can do your development using SSDT, if that's what you've been doing, and run your PowerShell scripts as much as you have been doing so far, both now on Windows and Linux. But we've also created real cross-platform tools that are our starting point, if you will, for this brave new world of extending SQL Server and the tools on this ecosystem beyond Windows. And that happened with Visual Studio Code, which runs both on Mac OS, Linux, and Windows. Not both, these are three, I'm sorry. And SQL Server Ops Studio. You've probably heard as MS SOS, Ops Studio, the popular name is still out. The fact remains that it is a cross-platform tool that you can use to run queries, to manage SQL Server, and also to do some degree of troubleshooting, performance troubleshooting using these cross-platform tools right there from your Mac, for example, or any other of the supported platforms. And we've even gone to lengths of making sure that, for example, if you are administering SQL Server and you probably have your scripts that run on a number of DMVs that collect information on the system, and probably they do some ingestion or they create some files, we have, like you would expect, support for Linux file paths, which are quite different from the Windows world. So, on top of all this, because SQL Server is an enterprise database service, we obviously need to support high availability for disaster recovery purposes and for disaster recovery purposes. So we have support for Pacemaker and CoroSync as two of the most popular high availability solutions to run on Linux. And that leads me to this slide here. So the state of the art on SQL Server in what relates to high availability is the always on technology. And this always on technology works both for high availability and for DR purposes. As you see on the screen right here, for example, I have a AG setup, AG always on availability group, set up between two Windows machines right there. One is acting as a primary with all my reads and writes, and I have a synchronous or asynchronous replica for read scale out with high availability on the other on another point of the globe or just in another point of my data center. But I can now extend, because we've extended SQL Server beyond Windows, I can obviously now extend these high availability solutions beyond Windows alone. So as you can see right there, I have another sync replica or async replica. You'll choose whatever makes sense for your deployment in another operating system, and it all works seamless in this architecture. So we have load balancing of readable secondaries in several parts of the globe, and you can have across operating system, and it becomes very flexible in what relates to what kind of solution you are deploying and how you are deploying it. And just to give you a real-world sense of how these solutions are being used, throughout the presentation we have a few of these slides that have first-person customer cases of how they've used some of these technologies to improve their business. For example, convergent computing had a challenge. They had a lot of operational expenses with hardware, with storage, and they had several tiers of workloads, as you probably may have in your companies. Tier 1 mission-critical workloads and Tier 2 workloads that may have different requirements in terms of throughput, in terms of compute. By moving from, as you can see on the left there, high availability solution based on always on Windows Server, they were able to have a distributed architecture incorporating Linux on white box servers, so low commodity hardware, cutting their ROI by 70%, which is quite incredible here. And because it's the same engine, it is a seamless migration in what relates to a database service from Windows to Linux and vice versa. You can take a backup and you restore on the other side, and you're done. So this greatly reduced the operational costs of convergent. Now, another feature I wanted to talk to you about has to do with in-memory OLTP. Who here is using in-memory OLTP in their database services? Anyone? Okay. So in-memory OLTP is a technology that we've released back in SQL Server 2014. And its main goal is to optimize the performance of high-throughput OLTP workloads. And with this, with these high-intensity OLTP workloads, you would expect more concurrency. And as you add concurrency to a system, traditionally, you start having bottlenecks. Well, when we developed in-memory OLTP back in 2014, and as we've been evolving the story of in-memory OLTP throughout the several versions, this has been on top of mind, which is remove the usual bottlenecks that are added to a system, to a database system with increased concurrency. And with SQL Server 2017, we have added more language coverage. We have increased the surface area, the programmability surface area within memory OLTP. And the benefits is that you can, for the most part, seamlessly move from on-disk tables to in-memory tables and unlock the performance of your data. So you can see, just as a representation here, a table that is working in memory is able to ingest data points from IoT devices, for example, at a high throughput rate, can act as a buffer, for example, before you move data to, for example, to a data warehouse, from where you extract the data and run your data mining algorithms. So a few scenarios that are useful for which we thought, if you will, the gold scenarios for in-memory OLTP are, like the name tries to suggest, high throughput OLTP. So very low latency 'for the gaming industry. We have one of our tier 1 customers, is in the gaming industry, so very low latency is key to the business. As a shock absorber, for example, if you are moving lots of data from your numerous data sources into a central database service, you need for that data ingestion to be friction-free. And for example, memory optimized tables can act as a buffer to ingest that data, on which you then run some ETL process to extract that data to somewhere else. But can be the destination. They can be, for example, the session state for ASP.NET, or even replace TempDB. For example, if you have a workload that relies heavily on creating and using temporary objects, TempDB, being a global resource, is still, architecturally speaking, is still a global resource that sits on disk. Now, you are able to leverage in-memory OLTP to replace these heavy operations that may be occurring in transient data sets to a structure in memory that is truly performant. And ETL, that's one of the last goal scenarios that I have here. You can create in-memory tables that are schema only, means that no data is kept in case the server shuts down, for example. Or you can have schema and data durability. For example, a schema only table is one of the key scenarios when you're moving data through an ETL process to make sure that you are absorbing all that data at a very high throughput to that in-memory artifact, from which then you are using other processes to put the data in its final destination. So it's very easy to use SQL Server in-memory OLTP. The first thing we need to do is make sure that we are using one of the latest compatibility levels. So in this case, to leverage all the surface area that we have in SQL Server 2017, I'm setting the database compatibility level to 140, which is the latest enabled. And then what I need to do is, because I may have transactions that involve both disk-based tables and in-memory based tables, and they have different degrees of throughput, of performance in a very concurrent environment, it is essential to use snapshot isolation. That means that we have writers are not blocking other writers and readers. So the other aspect is, as we can see highlighted in blue there, we need to set the database to be able to operate in snapshot isolation for the memory, for the in-memory tables. And then finally, I need to add a specific file group that will keep the in-memory table data for the tables I've created at schema and data persistence. Obviously, the ones I created as schema only are not persisted anywhere. So as you can see there, I need to add a file group as you normally would. What is highlighted there in blue is the only change to be able to support in memory, which is saying, hey, this file group will be the resting place for my in-memory tables. And then we move on to creating the objects. So creating a table is the same transact SQL statement that you are familiarized with the exception that you have there in blue, which is saying, hey, this table will be created in memory. So memory optimize equals on. And then I can just insert my records there. So as you can see, the changes from your familiar T-SQL to create and operate your objects are very similar, and it's a very short learning curve to start to use and leverage in-memory OLTP. Now, part of in-memory OLTP is not, or part of this proposition is not only where the data sits, but how we use that data. So you can continue to use your application with no changes, meaning if your application already uses a number of store procedures, functions, and other procedural code, you can go on using it without any changes, just pointing to the new tables which are in memory. But you can go one step further. We actually have the ability to create procedures and procedural code as native compilations, meaning that when you create a, let's say, a store procedure like you see on the screen here with native compilation, what we do is we pre-optimize and we create a set of disk-based files, DLLs, essentially, that will be loaded as you start up SQL Server. And whenever you call your store procedure to execute, we actually use that pre-optimized version that is very, very fast when it's working within memory OLTP tables. So again, you are already leveraging a lot of power when you're using your traditional transact SQL constructs with in-memory OLTP tables, but you can take it a step further by moving some of your store procedures and other code to natively compiled objects. So let me do a quick demo to really put together what this changing performance really means. I'll be running this out of my own laptop, which means that, as you'd expect, it's not very powerful, if you will. So bear with me that you'll not be probably seeing fantastic throughput. So what we have here is a simple application that's simulating a ticketing system, meaning that it's a website where people go in and buy their tickets for concerts, for shows, and this has been working for years under traditional T-SQL and also with on-disk tables. So as I start the workload, I see that the throughput here is around, let me try to bump this up, is around, oh my God, what is that? It's around 300 to 400 transactions per second. Again, this is running on my little old laptop. And this is running on traditional T-SQL, store procedures and whatnot, running on my on-disk tables. So for my laptop, this is not that bad. Now, what I'm able to do is, what if I move these underlying objects, the tables that this application is relying on, to in-memory tables, and I'm not changing anything else. I'm not changing store procedures or anything like that. Just moving the resting place of the data from on-disk tables to in-memory OLTP. So let me stop the workload here. And what I will do is, in this case, I'm recreating the table. So I'm dropping, in this case, I'm actually also using natively compiled store procedures. So I'm dropping the store procedure that's inserting data into my table. And I'm also dropping the table that has, one of the tables that supports this application. And I'm recreating that table, and as you can see, with a difference, which is memory optimized is on. Also, I'm creating a specific kind of index that is only available in memory tables, which is a non-clustered hash index. Now, this is effectively supporting the key that I have on this table. Much as you would have a non-clustered index on disk, this is the counterpart, if you will, for an in-memory OLTP table. So I'm going to recreate that table as in memory. As you can see, memory optimized equals on. And my durability will be schema and data. Obviously, I can't lose this data, right? So it will be sitting on disk, eventually sitting on disk, the data, but I'm operating only in memory. So with the throughput that I hope in-memory can provide here. And I'm also dropping my procedure, and as you can see, I'm recreating the procedure with native compilation. And one of the aspects of natively compiled store procedures is that I can only have atomic operations. So the keyword atomic there is very important. So as you can see, I'm inserting data into this table. So let me just execute this, and let's go back to our application and see what happens when I restart the workload. So you can see just by moving the destination of the data, I now have 10 to 15 times the performance out of the gate running the exact same workload. And this is possible with minimal changes, as you've seen, using, for the most part, familiar T-SQL, and I just move the table to be in memory, and provided I have enough memory on my system to hold that table as I created, you can see the difference in performance is quite astonishing. Question here.
Peter, we had a question here.
Do you have to recreate the tables? Could you just the alter table?
So the question is, do you have to recreate the table, or can you do an alter table? You need to create the table, recreate the table. So more lifelike migration from on this to in-memory would be, I would create the in-memory counterpart of the table with all the same types of constraints and whatnot that I'm using on this table, and then I would do a migration with a selecting to from the source to that destination. Yes. Okay. Any other questions on in-memory OLTP? Yes, there's a question there. What point does it get saved to disk? So as we are running this operation, the operations are getting logged, as you would expect. And it will be persisted asynchronously based on the log. So the log is still synchronous. You don't lose any data with that. Okay? Any other questions? Yes. So why did we change the database? Oh, so the question, if I understood, is why don't we use snapshot isolation level for the entire database rather than this table? Well, if you can, it's a good choice. One of the reasons that that SQL Server still hasn't changed the default isolation level to, for example, our CSI, is the fact that SQL Server runs on millions of data centers out there as in-place upgrades. So it's one of our features, quote unquote, is backwards compatibility, and changing mid-game is by a default is not something we would do. Now, having said that, with a properly architected system, snapshot, or at least read-committed snapshot isolation, is in fact a highly concurrent isolation level to be running your databases with, namely because in that moment, readers are not blocked by writers, and therefore you unleash that capability. Now, obviously, like you said, that can be used for the entire database. For in-memory tables, however, this is a requirement, and therefore you can use snapshot optionally just for the in-memory tables, while running, for example, with read committed on everything else in your database. Does that answer your question? Okay. So another feature that we've introduced some time ago that unleashes the power of data is columnstore, and the ability to store data in a columnar format. Now, this technology was introduced back in SQL Server 2012. And it's traditionally your tables, and as you create your indexes, your B trees, the data is stored in a row format. Meaning that when you read a row, when you need one record or a subset of a record, even though you may only need column 1 of your table that has 10 columns, when you read the record, we read the entire thing, to then retrieve only the column that you are trying to access with your select statement. Now, that may be, that is fine and actually very performant for short transactions. But if you are trying to do large analytical processing with aggregations that span a lot of data, that becomes an overhead, because you are now in that perspective reading a lot more data than you actually need to process. So back in 2012, we introduced, again, embedded into the engine, the ability to store and retrieve data in a columnar format. That means that when I'm accessing a table that has a few dozen rows, for example, and it has millions or billions of rows, and if I only need, in my select statement, to retrieve a subset of those and then do some calculations and aggregations on those, using column store means I'm only retrieving the columns, so I'm only reading. In fact, the I/O is only done on the columns that are relevant for my statement. This saves a lot of resources. But over this, column store is also a method of storage, like I'm mentioning there in the slide, which means that it's highly compressed, so we can fit a lot more data in memory as we are reading that data, and then as you are using it to retrieve and do your aggregations. So as a very high-level overview of what we do when we create a column store index on a table. You can see that for an existing table right there that has 4 columns, it's all in a row format. When you create a column store index on that table, we do a few things. We first divide the table into row groups, meaning that groups of up to 1 million rows that are grouped as still in all the rows. Still all the row is aggregated into 1 million records. And then we separate it into columns. So we divide those row groups into column segments. And then we apply a highly efficient compression algorithm on top. And as you can see there, the compressed column segments have various degrees of compression because that will, like any compression algorithm, is directly tied to the type of data you have. As more repetitive the data becomes, for example, you are able to achieve higher levels of compression. If, for example, you are working with a encrypted database, well, by the nature of encrypted data, you have less repetition, and therefore, you would achieve different ratios of compression. So the key benefits of using column store is that we typically provide 10x, if not more, of data compression, which is awesome for data warehouse deployments because it saves cost tremendously. But then by indexing on columns that have very repeated values, you are able to also compress a lot of those column segments and save a lot of performance and gain a lot of performance by that because you do less I/O to read the data into memory. So more data fits into memory, therefore you need to use disk less. And on top of this, we have also introduced batch mode execution. And batch mode execution, what it does is on top of the traditional row store technology, which, like I mentioned, reads the data in rows, we are now able to process in batch those segments that come in. And for example, the aggregations that you do over wide sets of data, they become much more performant. So the steps to create a column store index, and in this example, a non-clustered column store indexes are real simple. You know probably the notation to create a non-clustered index. You just add the keyword column store. Done. And you execute the query as you would, and you can see this query is one of the gold scenarios for users of column store because it has a number of aggregations and groups. A number of aggregations in the sum, in the group by, you calculate averages. So this all fits the gold scenario for column store indexes. And you can verify if the index you've just created is being used by your workload through a number of system views, for example, the sysdmdb index usage stats that will tell you how many times that index was used over some other index on the table. So you can actually bring all of this together, meaning you can bring in-memory OLTP and column store together in SQL Server 2017 to provide high throughput data warehousing environments for your data. Meaning we can create a column store index over an in-memory table, and with that unleash the power of these two technologies combined. The key benefits would be you are able to, with minimal impact, you are able to mine data and run reporting workload over OLTP operational data that sits in an in-memory table. And this becomes very, very powerful for technologies such as self-service BI that then are able, with no other change done at the application layer, they are able to just bump up the performance as we've seen in that quick demo before. And there's a question there. Yes? I'm sorry, can you repeat? Yes, so the question is, can we turn a non-column store table into a column store table? Meaning, can you create a column store index over an existing table? Yes. So there are different types of column store index. There is a clustered column store index, and there is a non-clustered column store index. the clustered column store index needs to be, so if you create a clustered column store index, you cannot have non-column store indexes on the table. Now, the case I've just mentioned here, which is creating non-clustered column store indexes, that you can create over over tables that, for example, have a clustered index as a primary key, if that answers your question. There's another question there. So the question there is, what if the table grows beyond the memory that you have available on the server? Well, you have a few ways to deal with this. The short answer, meaning you won't get into that scenario. The longer answer is when you create an in-memory table, as you've seen in the notation before, I created a hash index. And the hash index has a predetermined number of buckets, because it is, after all, a ginormous hash table. Now, my table will not be able to grow beyond that number of buckets. So what I need to do when I move to in-memory tables is really understand before heading there, what is the foreseeable size for the data that I want to fit into an in-memory table. And once I do that, I obviously need to architect my system to have enough memory on the system itself to hold that data, but I won't be able to grow the table beyond the ceiling of number of buckets I've set. And therefore, you won't be able to get into that. Now, we have other ways of dealing with this. For example, if you have, if you have over-architected your system, or meaning if you have over-provisioned your system in terms of the number of buckets in all your in-memory tables are above what your system can hold in terms of physical memory, you can use, for example, Resource Governor to create resource pools with specific memory caps on those tables. Again, your system will not run out of memory. Your tables will get to a point where you can't insert more data, and those will become, in essence, read-only. So you need to deal with that. So it's very important, thank you for the question, because it's very important to, let's say, pre-architect the intent on which we're trying to create an in-memory table and create it with that end in mind. So don't create an in-memory table that you think you'll be keeping for years with the next 2 or 3 months in mind. If it's a table that will support your business in the next 5 years, architect for those 5 years. So Atom Data Solutions, for example, had a challenge, which is they had a large ETL process that extracted data from a number of data sources, non-relational data sources, and they had to do a number of aggregations and insert that data into the data warehouse. And this was about 12.5 terabytes a day, and the whole ETL process was running in about 24 hours. Now, they were able, by leveraging both in-memory OLTP and column store, only by doing that, bring the same ETL process down to less than 3 hours, and what used to be a 12.5 terabyte data set became a 4.5 terabyte data set. So the column store compression technology really helped in saving costs and time, as you can see here. So, and I will speed up a little bit because I'm running tight on time. Other technologies we've introduced in SQL Server 2017 have to do with adaptive query processing, meaning the ability to optimize how queries are executed. Now, traditionally, in SQL Server, when we execute a query for the first time, the query is optimized with the metadata and the statistics that we have available. The query optimizer optimizes that query, creates a query plan, and then the execution engine takes that plan and drives it to completion to return your data sets. Now, what happens in a scenario where that initial compilation and optimization was done under wrong assumptions, meaning with wrong data? Maybe the statistics on your tables no longer represent the underlying data distribution, and therefore the engine optimized with one data distribution in mind, but your tables reflect otherwise. So this and other such fixed outcomes were possible in SQL Server, and that could lead you to all sorts of performance problems. So in 2017 and Azure SQL Database, we've introduced the notion of adaptive query processing that we are taking to a whole new level in the VNext of SQL Server and as we continuously evolve and deploy for Azure SQL Database. So a quick example, just an overview, is I run a query. And before, in the before scenario, meaning before SQL Server 2017, I have chunks of my data that have to spill to disk. And why is that? Because as I write my query and execute it, and the query optimizer optimizes and produces a query plan, the immediate result of that optimization is, hey, I'm a query that needs to run. I need to grab me some memory in order to execute. That's fine. The point is, the memory that it grabs before starting execution, because it's based on a fixed optimization, it's also a fixed amount of memory. So if I'm estimating that I need 2 megabytes to run my query, but in the end I would need 5 or 10 or 500 megabytes, guess what happens? That you still run your query, but the excess memory is now being turned into I/O, into TempDB, into spills to disk. So with adaptive query processing, what we're introducing is the ability to learn from these episodes, these executions, and then be able to adapt to those realities, and in subsequent executions, be able to adjust a number of resources and strategies to join your data, and what kind of resources we take from your system to run your workload. Effectively, being adaptive to the workload as it progresses. And this is a reality already in SQL Server 2017 and also in Azure SQL Database. But we also have other capabilities that you probably heard in other sessions in this conference this week. The ability to do auto-tuning. Now this, for example, if you were in Rowan's session a few hours ago, Lara Rubelke showed how auto-tuning is a technology that's available on Azure SQL Database to provide ongoing tuning in what relates to your database design. Now, we have also brought to SQL Server 2017 some of those technologies, namely the ability to automatically fix some problems without human intervention. Now, be advised that human intervention is still possible. If you are a DBA or a dev that really wants control over this entire process, you can have it. You can turn off this adaptive tuning. But what you can see as a representation here on the screen is, in this timeline, a plan was created and executed for whatever query that you're running. And it runs with an expected level of performance and runtimes. Now, at a certain point in time, let's say you created a new index, or you dropped an index, or you updated statistics because you've done a large number of inserts or deletes, and the data distribution changed. The point is, the engine needed to create a new plan to reflect that new reality, if you will. So you see plan 2 there. Now, at another point in time, the system needs to, because of one of these changes, re-optimize the plan. And the first execution that comes in is something that skews heavily the performance of this seamlessly the same workload. As you can see, performance tanks as execution times go up. If turned on, automatic tuning is able to detect these occurrences, and because there's a previously known good plan, it can automatically revert back to that plan and use it without human intervention. Meaning that if you are a DBA or a dev that supports production, nowadays with DevOps models being the new de facto standard, you can actually avoid those middle of the night calls saying performance tanked in this critical system, and you need to wake up, go online, try to understand what's going on. You can actually come the next day to work and understand what went on, but as you were sleeping, the system fixed itself. So I'm just going to run a very quick demo on this, so you see how powerful it is, and if I'm handling my system overnight, this can really help. So again, this is running in my little old laptop. That's why we have about 20 to 25 batch requests per second. Not a lot, I know. And we're running our workload here, and at a certain point in time, a regression may be introduced. So I introduced a regression in my workload, meaning I had to recompile the plan, and the first execution actually turned into a different a query plan that's not optimized for most of my workload, but only for that first execution that came in. So you immediately see that throughput is going down. Now, actually, let me stop this because the graphic became quite unusable. So let me reset this, start again. So again, I'm running my workload happily. It's within my expected performance, whatever it is. and you see there 15 to 20 batch requests per second. So at a certain point in time, I introduce a regression, and what happens is performance tanks. Because as you'll see in the next few moments, the number of batch requests per second went down to less than 5. So this can happen in a real system. And what happens at this point is if you connect to the system, you are actually able to understand if there are any recommendations. And for example, going into this system DMV, the SysDB tuning recommendations, I'm able to see that, hey, in query 69. So what I'm able to see here is, average query CPU changed from 169 milliseconds to almost 1 second per execution. And be advised that the automatic tuning option is not enabled. So I'm not able to, me as a system, I'm not able to fix this automatically. But what happens is, if I actually had turned on auto-tuning, the system would detect that this regression occurred. And as you can see there, it restored the previously known good state in terms of throughput, and I'm back to the expected number of batch requests per second. This was done without you ever intervening in the system, but you can come back in the next morning, and as you look into the same recommendation, it's not here anymore, but you have other objects that you will be able to see if what recommendations were at play and what happened by going to Query Store, which is the flight recorder you have for your system, to understand what went on. So, any questions on this? Okay, and just as a last couple slides here, we did mention that we are obsessed about security, and we have a number of technologies around security that really can really secure your system and your workload. For example, we have Always Encrypted, which encrypts data in use, not only at rest. So, for example, you see here that through the client library, SQL Server now gets its table encrypted. For example, I have the credit card column in this table is now ciphered, which means that me as a DBA, even as a sysadmin, I'm not able to come into the system and read this data. And however, a client can still issue the query, and the query is running, for example, is asking, for example, customers where the credit card number is X, which is obviously something you don't want to keep open in your database. But once it goes through the client library, so this is all controlled at the client application level, what SQL Server sees, if someone is sniffing or running a trace on SQL Server, what they see is a ciphered value, as you can see there. So if you are a sysadmin and you are looking at the workload, there's no way you can read that encrypted data. And as you can see there, what SQL Server Engine did was it returned a result set with ciphertext that was only unencrypted or decrypted at the client level. And that's when you create the result set. Now, other technologies have to do, for example, with dynamic data masking. For example, if I have data in my database that's clear, but I don't want to show it to my end user application, for example, in a call center. If someone asks you for the last 4 digits of your social security, they're not seeing your full social security because you can mask that at the database level as the application connects to it. We also have role-level security, meaning you can create profiles of data access over the same data. You can create profiles that access only subsets of that data depending on the incoming connection profile. And obviously you have transparent data encryption, which is data encrypted at rest. Yes? I'm sorry, can you repeat that? The equivalent data type for what? So the data, I didn't change any data type in any of these. I didn't do any kind of change in my table. There was no change in the data type. We can take this offline and I'll explain how it works. Yes, so Nelly, I'll give it. Can we please take it in the end because we're running short on time and I think I've taken most of Nelly's time.
It's okay. I think that you guys seem to be awake, most of you. All right, let's talk about Polybase. So how many of you have used Polybase? It was introduced in SQL Server 2016. All right. Let's see. So basically, Polybase is a technology that was introduced in SQL 2016. And it allows you to access data outside of the database, still using the T-SQL language. So, for example, it allows you to run queries on external data, such as data in Hadoop, and import and export data from, for example, Azure Blob Storage. So it sort of gives you an ability to reach out to external data sources, but still use T-SQL and not need any type of new software to do this. And if we look at some of the capabilities, for example, if we talk about data virtualization over Hadoop data sets. So what we're talking about there is what I mentioned, simple T-SQL query to query HDFS data sources, such as Hadoop. No new software is needed. You can also push computations to the Hadoop storages using Polybase. So the thing is that you don't really need to worry about this. The query optimizer will make a decision on when it makes sense to actually push down the compute to the Hadoop storage versus not doing so. And it does that based on it's a cost-based decision, and it does that based on some statistics on the external tables that you're creating. And when it pushes down, it's actually generating MapReduce jobs to be able to handle the execution. And if we go down to sort of scaling out, you can actually use Polybase over Hadoop to scale out your computation as well. So if you want to improve, for example, your query performance, what you can do is that you can create SQL Server Polybase scale-out groups. And what that does is that it enables the parallel data transfer to basically a cluster. You could have a cluster of Hadoop nodes and transfer the data in parallel. So this basically enables you to query these external resources faster. But then I would say most importantly, when you talk about Polybase, and let's say that you're still using your Power BI dashboards or other type of reporting on top of your SQL Server data, one of the biggest advantages is that you don't really need to change anything in the reporting or dashboard layer. From a dashboard perspective, you're just querying SQL Server data, even though you're querying these external tables. So you don't really need to make any other changes to your dashboards and so forth. It's just that you create these external tables over the external data sources. Okay. And this is just, probably skipping through this. This is just an example of how one customer, an insurance company, used Polybase to access heterogeneous data sources and sort of create some tailored policy rates. And that had a positive impact on the revenue. But basically, let's move to something more interesting. So we introduced Polybase in 2016, and we're now making some investments for SQL Server vNext to extend the reach of Polybase to a new set of data sources. So we're adding some new connectors for Polybase in SQL Server vNext, which will allow you to then create external tables over Teradata, Oracle, and MongoDB sources as well. And if you are interested in this and want to hear more, I suggest that you come and talk to me, because we actually have a private preview of this right now. So if you're interested in trying it out, I can connect you to the program managers that are running this preview. So please come and talk if you're interested in that. Now let's jump to the topic of machine learning and machine learning services. And I'm very curious to know if any of you have played around or tried out SQL Server machine learning services or R services that was introduced in 2016. Anyone? Okay, we have a couple of people here. Okay, great. So then I think this will be an interesting topic. So as I mentioned, in SQL Server 2016, we introduced R services with the R integration. So R is a machine learning and statistical programming language. With 2017, we introduced Python and renamed this feature to machine learning services. Now, both of these are integrated tightly with the SQL Server engine, but we have done this integration in a way so that we can still execute these external scripts, this third-party code, securely next to the SQL Server process. And we don't have that much time to explain the architecture here, but I'm happy to talk to you offline about this. It's basically that we introduced a new framework, an architecture called the extensibility framework. And this framework allows us to do these type of executions more securely and not randomizing the SQL Server process itself. And by default, we're only giving these external processes 20% of the server resources. But this is something that you can tune using resource governance and external resource pools that we introduced in 2016. So how does it look when we run R and Python in the database? It's basically that we have wrapped the Python scripts and R scripts in a special stored procedure that's called SP execute external script. So when you embed the R or Python script, you can push any type of SQL query into this stored procedure, and you can get your result set back. So it's basically sending the data into a data frame into R and Python in those runtimes, and it's sending you then the result set back. So this is basically how it works. And now let's talk about some scenarios. So there are different sort of customers or types of customers or users that would use this. And one of the personas that's interested in data science in general are data scientists. So the idea here, do we have any data scientists in the room? Okay, nobody. Okay, then I can skip through this fast. But basically the idea is that data scientists, they have, if you think about the process of data science, it's basically you start with some exploration. You need to explore your data, get to know your data, do some plotting, understand it. And based on that, you might need to train a machine learning model. So a data scientist wants access to the data. Now, one of the advantages of having these workloads close to where the data lives is that the data scientists can still work against the database. They can still, run their scripts, do some querying of the data. The data is in SQL Server. They don't need to move the data, because that's actually one of the things that data scientists like to do. They like to extract the data from the database, and that has security implications. So there's no need really to move in this case, because we have the possibility from the client workstation to push whatever computations that they want to do on the data to execute on the server. So they can still work from their favorite IDE. It could be Jupyter Notebooks, PyCharm, RStudio, wherever they like to work, and just script against the database. The execution happens on the server. They can leverage the power of the server itself. It's usually, a bigger box than their laptop. And then they can get the results back. So if you look at the values for data scientists, and in most enterprises and organizations, you're starting to see that more and more companies are hiring teams of data scientists. It's hard to find them, but I'm trying to train, developers into working against, these type of workloads and processing. So basically, they can still work with the full data set. Don't need to just extract a sample data set. It's more secure. They can work from their favorite IDE. And they can, most importantly, you can work with any open source framework or package still using R and Python in database. So there's no limitations. Even though we are providing our own Microsoft proprietary algorithms that ship with SQL Server. You don't have to use them. You can still use anything open source. You can do deep learning on TensorFlow. You can use any type of open source R package that you want. And you can leverage some of the scalable Microsoft algorithms that are part of this integration, which enable you to run parallelized processing on your R and Python. For example, you can parallelize training and scoring that way. And also, of course, the model deployment. This is one of the pain points in many organizations that we hear, is that oftentimes data scientists have to code something in R and Python, and then once they want to deploy something in production, it's not really clear how an application in production can access these type of models and scripts. So the challenge there today is, how do they deploy this, operationalize this? So by having it in SQL Server, this would probably be the biggest key value of this feature, is that there's no need to recode whatever R script or Python script they had, for example, into Java or something else, into Ruby, just because they have an application that understands that. If you wrap it into the database, you store your model as a binary object in the database itself, any application can access data, tables, stored procedures, and these type of things. So that's the way that you would operationalize these type of scripts. And also model version management. You can have thousands of models with different versions. So this can be a tool of collaboration too, working against the database. So basically, what we're saying is that SQL Server, if you already have a SQL Server in-house, why don't you let SQL Server be the end-to-end platform for these type of workloads? There's no need for an additional analytics server where you host these models and these type of scripts. Now, from an application developer perspective, or a database developer, or any type of developer, how do you get your application to consume these things? Here we have the same type of principle. You call a stored procedure. The execution happens on the server, executing Python in this case, and you get the results back. And any application can call a stored procedure. So that's the idea of this. And just quickly through the values for the developers is that, you can consume this type of intelligence into applications. You can get your predictions, store them in a table, and just read them from a Power BI dashboard. And you can make this available to a bigger group within your organization. Data engineers and DBAs can also do just general purpose processing. Python is not only for machine learning, for example, and R as well. You can do just general purpose processing in Python or R where it makes sense, instead of just using T-SQL. So it's just another capability. And you can do very powerful visualizations too, and you can maybe do plots over some performance in your database, just general, how much space do you have left, how are you utilizing the storage on the database. These type of things can easily be plotted just with Python to get a better idea. And then also, as I mentioned, we wanted to do this in a secure way and a manageable way, so we have resource governance and ways to control these things. And all the executions are being executed on the server by low-privileged users that are created today during the setup. And we're also bringing this feature to SQL Server on Linux. So for vNext, that's what we're working on. And also porting this to Azure SQL Database is one of our goals, because this is currently only on SQL Server on Windows on-premise today. I will skip this. This is just a customer example where a customer managed to reduce their training time significantly, and by basically moving everything into the architecture of doing training and scoring predictions in the database versus having it outside, and just simplify the process a lot. Now let's take a look at a demo. And I think I was number 8. Yeah. All right. Let's see here. So this is an interesting demo. This is a text classification problem. So when we have classification problems, it basically means that we want to classify something into, if it's a binary classification, it's either like yes or no. or in this case, it's a multi-class classification, which means that we have, let's say that we have some customer support tickets, and we're getting them in. It's a bunch of text, and then we have a subject. Now, we want to classify these into, label them into like subjects, so we know what is this support ticket about. And in that way, we can sort of route these to the right teams. Now, this data set that you're seeing is not a customer support ticket data set. It's just an open data set, but the structure is the same. So as you can see here, I don't know if you see this. This is a subject, and then this is a bunch of text. And this dashboard just basically shows what type of labels we have and that are occurring, what type of subjects, and what text was sort of belonging to which label. So, as a data scientist, let's pretend that I'm a data scientist, and I'm working against a database, like the first picture that you saw. I'm working in my favorite IDE. I'm using a Jupyter notebook in this case, and I want to just step by step in my notebook run through the different, just look at my data, understand it, and so forth. So what's happening here is that I have some Python code here, but I'm also defining something that defines a SQL Server compute context. This means that by having this, I can run some of these computations. In this case, I'm running the open source, I'm using an open source library, and I can push the computations to the server. Now, this is my data set. In the next step, I just want to, this is how they work. I want to look at my data. I want to understand it. In this case, I want to create a word cloud. And I'm using an open source package to create the word cloud. But I don't want the actual generation of this, the actual processing to happen on my client. So then I can use the SQL compute context, and I can say, I want to push this part to the server and execute this on the server. And I'm plotting my word cloud this way. In a similar way, I can plot different types of graphical representations of my data to understand it better. Now, once I've done that, of course, I want to do this solve this classification problem. And by doing that, when you work with text, it's very common that you featureize the text. So I'm using one of the Microsoft ML packages to featureize the text so that I can use those features to train a model. So that's what's happening here. This is a featureized text function as part of the Microsoft ML package. And if we jump to the actual model generation here, we're generating a model, a logistic regression model using the Microsoft ML logistic regression algorithm. And what's interesting here is also probably the most important part. I'm pushing the training, which is a very heavy computation. Trainings can take days, sometimes weeks, if you have large amounts of data. So getting the most, sort of doing that on a powerful server is a big advantage. Now, I've done the training. I wrote the model as a binary object to the database. And I can also do some scoring and evaluation here. Now, quickly, before we run out of time, let's take a look at how this looks once I'm ready to operationalize this in SQL Server. Now, as I was showing previously, you saw that slide with that code, Python code. So here I have an SB execute external script stored procedure. In that, I have the exact same Python code that I was running with the exact same training algorithm. I have my featureized text here. I have my RX logistic regression call. So what's happening here is that I'm writing this model here into a table directly from my Python script. And if I would look into this table here, I would be able to see, it doesn't make sense, but it's a var binary object. That's my model. I stored it there. I can version it. I can work around. I can operationalize my model this way, make applications access it. And now, if I'm ready for the scoring is basically another word for making the predictions. In the same way, I have, my Python code here. It's long script in this way. And as you can see, currently there's no support for text highlighting. So working in your IDE, maybe in Visual Studio or somewhere else, it's much easier to troubleshoot, because once you are ready to operationalize, that's basically when we recommend moving it into the database. And this is not something that I would say the data scientist alone will do. like the data scientist will depend on a SQL person like a DBA or SQL developer to do this step. So this is a joint thing. And that's something that I think is a learning for a lot of companies to realize that, that these two type of roles need to work together to make these projects successful. Now we had that, let's now execute the scoring on a small data set just to take a look at it. So basically now I'm running it in SQL Server. It's running the scoring. It's writing the predictions into a table. And in this way, you can basically write the predictions during the night and then let the dashboards in the morning select the newest predictions, for example, that you had. So what you see here is that you see the label, you see the predicted label, and what a logistic regression does is that it gives a probability of a specific label. So the highest probability is the predicted label. Yeah, so I hope this made sense to you and you think this is interesting. If you want to hear more about this, please come to talk to me and submit. We're the PMs for this feature, and we're looking for customers to work with and in closer engagements. So just come up and talk to us if you're interested. And I think that pretty much sums up what we had, right, Pedro? Let's move back to this. And also, if you are here on Wednesday, I wanted to recommend you to go to a session of one of my colleagues. It's called DevOps with SQL Server on Linux and containers. So if you're interested in that, that's a session on Wednesday at 8:30 in the morning.
And thanks for sticking around a few minutes after time. And have a great conference.